Alright, welcome to the third video of this series, and as you can see from the title, we're going to be talking about a diode, and specifically it's going to be a half-wave rectifier. Alright, so a lot of stuff to cover. Everybody's seen the diode symbol here, right? So you look at a diode and you look at it and there it is. Sometimes you might see the diode, you might fill this area here in, make it solid, okay? And you hear people say, well, the diode is like a check valve. It's an electrical check valve. It allows current to go through one way but not the other way. But they always don't never explain in detail about if you can look at a circuit, could you tell if the diode was turned on or if it's turned off? Well, we're going to cover that so you'll be able to know. By the time you finish watching this video, you know everything you need to know about diodes. Alright, the diode is a two-terminal device. That's where it comes from, diode. Di means two, ode means terminal, or if you want to, you can think of it as electrodes. So, it's a component that has two terminals. Now, you notice how it has an arrow and it's pointing in this direction? Well, that is the direction of conventional current flow. So this is where it will turn on if the conventional current flow is going in this direction. And of course that is from positive to negative. Alright? Now the diode is a silicon type material. It's made up of silicon. Okay? There's our two terminals coming off. And we can divide it up. And this side over here, by the way, is called the anode. This side over here is called the cathode. Now if we take this here silicon and we add an element to it such as phosphorus, and then if we add it to here, we're going to get an excess of positive charges. So we're going to have a lot of positive charges on this side, which is for the anode. And this is a P-type material because this P stands for positives because we have a lot of positive charges. Now over here on this side, this will be the cathode side. And we're going to add another element, such as aluminum, and we're going to add that over here, and that's going to give us a lot of negative charges. Alright? Now keep in mind that with the negative charges over here, there's going to be a few positive charges. And over here, where the positive charges, there's a bunch of them, there's going to be a few negative charges. But for the most part, we're going to have an excess amount of positive charges here, and we're going to have a lot of negative charges over here on this side. Alright? And this over here is an N-type material, N standing for negative. Alright. Now there is one thing that you need to know, to remember, that if you look at a circuit and you'll be able to tell is a diode turned on or off. Do you remember when you played with magnets and you remember how they attracted each other and they repelled each other, right? So if you take, for example, like say, if you take a north and a south pole, you know, they come together, okay? So that and that will come together. But if you take light poles and you put them together, then they're going to repel, like two norths or two souths. Well, that exactly holds true for charges. If I have a plus charge and a minus charge, well, they will attract. And if I have like charges, such as two positives, well, they are going to repel. And if I have two negative charges, like, of course, then they're going to repel. Remember that? You got the diode. You got it down pat now. So, let's go back and look at this right over here. Let's say I'm going to take this diode right here. And by the way, see, this would be the P-type material over here. And this is the N-type, right? Just right down here. Now, let's say I'm going to take this here and I'm going to hook it up to a battery. Okay? Now do not hook up a diode directly to a battery because you have to limit the current through the diode, otherwise it'll burn up. I'm only doing this to illustrate how the diode, how we can look at it to see somewhat how this here diode works. Okay, this is our plus, this is our minus. We take the positive charges that's coming out of the battery, and you can see that the positive here is going to be repelling the positive charges that's inside the P-type material. So you can see that these positive charges are going to go in this direction towards this line right here, which is called a P-N junction. This is where the P and the N-type materials are together. And then over here on this inside, you can look over here, you see the negative comes up out of the battery, and you have the negative, and it's repelling the negative charges that's in the N-type material. So that is being pushed along in that direction. Or do you see how the two arrows are coming together towards the P-N junction? Well, when you see that, that means you're going to be crossing the P-N junction, and now we're going to have current going through the diode. This is when the diode is turned on, or it's in a forward bias condition. You can think of the diode like a switch. In fact, one of the approximations you can look at, the first approximation is looking at it as a switch. It's either closed or it's open. All right. So let's go back and let's do this. Let's go ahead and let's reverse these connections. Now we have a negative here, negative there, and positive over here. Can you now see that the positive charges that's inside the P-type material is being attracted to the negative? Remember, unlike charges attract. So now these positive charges are being pulled in this direction, and look at the negative charges that's in the N-type material. They are being attracted to the positive charge over here from the battery, so it's going in that direction. So in other words, these charges are being pulled away from the P-N junction. When you see that, then you know the diode is open. It's just like an open switch. And in this condition, then the diode is reverse bias. We all good so far, right? Simple. Now, is that the way a diode really works? No. This is probably maybe 40%, if that much. For me to cover exactly what happens to the diode and how it works, we got to go down to the atomic level. And we got to talk about a lot of new terms, and it will probably take 30 minutes just to cover how the diode works in actual reality. But for our purposes, just knowing this right here, unlike charges attract, like charges repel. And if you can remember that the anode is the P-type, the cathode is the N-type, then you got it licked. You can mentally think about how the charges, what will happen if you hook your battery up, and you will know if that diode is turned on or is it turned off. All right, let's take a look. Let's take a look at an actual circuit. Let's say I have a DC power source. Here's my diode, and here's a load. Let's say it's a little test light. And let's say I put 12 volts DC over here. All right. Now you can look at that. I know right now, is that diode turned on or is it turned off? Remember, here's our anode. Remember the anode is P. The cathode over here is the N-type material. Just follow it out. Positive charge, positive, pushing away. N over here, see, from the battery, pushing that way. So the two charges are coming across the P-N junction. That means this diode is turned on. All right? And this light bulb will light up. All right? And if I was to take and reverse these connections, can you see now that the negative here and the positive attract? So now it's going to be taking the positive charges out of the P-type, pulling them this way. And then over here we have the positive coming up. And you can see that the N-type material, the negative charges in it is getting attracted to the positive from the battery, getting pulled away. So now they're pulling apart. They're not going to be crossing that P-N junction, so at that point, the diode is going to be open. Okay? I think we got it. I think we got it now. I believe you guys got it. All right, so let's analyze it a little bit. Okay, I got my 12 volts DC over here from my power source, right? Now the diode is already forward bias. It's turned on. Remember, if it turns on, think of it like a switch. If it's closed, that's forward bias. Forward bias. And if it's open, that's reverse bias. All right? Now, the diode has a resistance built in it. And it's called, if I could take this here PN material, and if I could take the P material by itself, and if I put an ohm meter on it, I will get a resistance, and that resistance is called the ohmic resistance. I can do the same thing with the N. If I put my ohm meter on it, got resistance, ohmic resistance. If I take these two resistances and add them together, then I got what's called bulk resistance. So all the diodes will have a resistance, and it takes so much voltage for that diode to turn on. And it takes approximately, for silicon, it's going to take about 0.7 volts. That can vary, it can go from 0.5, 0.6, 0.7, maybe a little more, but 0.7 is the general rule of where you look at of where the diode turns on. Okay? Now because of that resistance, as the current increases to your load, if you put a heavier load on it, that means that the voltage drop across this here diode is going to increase, right? More current through a resistor is going to cause a bigger voltage drop or larger voltage drop. So we got to keep that in mind. 0.7 volts for the diode to first turn on. That is kind of the general rule, but that can vary just a little bit. So if I have 12 volts right here on this side, and on this side, if we take off 0.7 volts, then over here we should have 11.3 volts DC. And if I put my voltmeter right here to measure DC volts, that's what I should get, 11.3 volts, approximately. Okay, this is a circuit that we just talked about on the whiteboard. So let's go over it real quickly here. We have the DC power supply. I have it set for 12 volts. Now if we take and look at the positive terminal here of the supply, you can follow it out. You go on the red wire, and we come into right here, and this is connected to the anode of the diode. And then over here on the other side, the cathode, which has the band, is going to go along, and it's going to go to one side of the light, the test light. We coming off the other side of the test light, and we're going right straight back, and we follow the black wire, and we're going right back to the negative side of the DC power supply. So basically just this diode is wired in series with the test light. Okay, I'm going to turn on the power supply. So take a look at the test light when I turn it on. Now as you can see, the test light is on. So we have this here diode in a forward bias condition, where basically it's just like a switch, as we talked about on the whiteboard. Now I'm going to reverse the polarity of the power supply, and we should expect the light to go off. So I'm going to do that now. So I'm going to pull out the red lead, the black lead. I'm going to put it over on the positive. So I'm just reversing the connections. The power supply is still on. If you take a look over here at the light, you can see that the light is out. So now let's go back. Let's reverse our connections again. Now you can see that the light is on. Now let's take a look at some voltages. I'm going to take a look at the voltage that's coming directly out of the power supply. I'm on the anode of the diode, and I'm on the DC negative of the power supply. So I have 12.03 volts. Now let's go over to the other side of the diode, and you can see I have 11.25 volts. This 11.25 volts is what's feeding the test light. Now you can see there's a voltage drop. So this voltage drop is a drop that's across the diode. If I want to measure that voltage drop, and you remember it should be somewhere between 0.5 to 0.7 volts. So let's see what kind of voltage drop we have for this diode. As you can see, we have 0.783 volts DC. That was simple, right? All right, let's step it up a little bit. All right, let's go to AC. Now for AC, let's just say we're going to use a transformer. All right. Here's my primary winding. Let's say I put 120 volts AC. There's my iron core that my windings are wrapped around. And let's say we got 12 volts AC. Now that 12 volts is measured between this outside leg and let's say this outside leg. Okay? Alright. Alright, so now we're going to put our diode in. And now, here's our light. Alright. This is going to get a little bit more complicated than just that standard DC power source that we have. Because now this voltage is constantly varying. If you remember from our other second video that we did, remember we have the AC, it's going up, it's going down, right? Now, there's our AC. That's right here and there. As this is going up, this is positive and this is negative. So as this is going up, say positive, this one down here is going negative. So it is 180 degrees out of phase between the outside legs. Alright? So instead of me drawing the little waveform right there, I'm just going to put plus and minus. So right up here, I'm going to put let's put 12 volts AC right there. Here's my plus, and here's my minus down here. Remember, 180 degrees out of phase. So as this is positive in this area right here, then you can see the diode is going to, what? Turn on or turn off? Right, so it's turned on. There again, think of the diode as a switch. Throw the diode symbol out if you want to. Close it, and there's a switch. So now it's going to come through the diode. Comes through the light, and it's going to return. Right? So now if we look at that, on this here, if we was to look at this on a scope right here, we would see, and let me just go ahead and draw. In fact, let me see if we can make a little room. First we're going to start off with our AC. Okay, this is what we got right over here. Here's our 0 volt line, right? Now as this goes positive on this side, this diode is going to turn on. So right here on our DC, this is our output, measure right out across here, then we're going to see this first half cycle right there. Okay, now we come down to here. Now we reverse direction. Now this has become negative, and now this has become positive. Okay, now you see the negative is going to the P-type material. Remember, negative, positive. Now they're attracting, pulling the positive charges away, and it's doing the same thing. It's pulling. So they're not crossing the P-N junction. So now this here is open. Think of it like an open switch now. No current's going to flow. So here is our 0 line. So this is what we're going to get. Right there, we got it. Right here, that's when it turned polarity, and now we have this, 0 volts. But look, it comes back up again, positive. So now this goes back to positive, this goes back to negative. Now we forward bias the diode. Now we come back up again. And the polarity reverses, goes back to 0, polarity reverses, then we go back up again. Now, notice that from here to here, that is one cycle. But look down here, we're only getting half of the cycle. That's why it's called a half wave rectifier, because it only conducts on one half of the cycle. Right? Pretty simple. Alright. So now, let's take a little look at this and see if we can analyze this a little bit. What do you think would be our DC volts out there on across this here load? Well, if I look at my 12 volts AC, I got to start off with my peak voltage. And if you remember from the previous video, the voltage peak is going to be equal to the RMS voltage times the square root of 2. Voltage peak, what's RMS? It's 12 volts. And the square root of 2 is approximately 1.414. And we come down to here, and what is that going to give us? That will give us 12 times 1.414, and I got 16.97. 16.97 volts peak. Remember? That's our voltage peak. RMS is about 70.7% of peak. Alright, we still ain't got to our DC volts yet, but we got to figure out the peak voltage first. Now we got a drop, a voltage drop, remember, about 0.7 volts. Well, let's take off 0.7 volts. So now we're going to say voltage peak, 16.97, subtract 0.7 volts. What does that give us? Minus 0.7. Now we got down to 16.27 volts, okay? That's what we got now. That's, of course, this is all AC, right? Now we take that voltage. Now, remember, that's what's going to be out here. 16.27 volts peak. Remember right here where we draw the AC, boom, 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 right? Well, that voltage right there, that is at 16.27. Okay? But what is that going to give us for DC? Well, this is where this shows how bad this half-wave rectifier is in efficiency. Because with all of that right there, well, first of all, we didn't get the negative cycle, so that was wasted. But now we're going to have to take, get the voltage DC out. We take the voltage peak and we times 0.318. In other words, we're taking 31.8% of that peak, and that's going to give us what our DC out voltage is. So if I take my 16.27 volts peak times 0.318, my volts DC is going to be times 0.318, and I got 5.17 volts. 5.17 volts, that's all I'm getting out here across that light bulb. Alright, let's take a look at this here half-wave rectifier, and this time instead of using a DC power supply, we're going to be using an AC that's going to be feeding the diode. What I have here is a center tap transformer. I have on the primary, it's going to be feeding 120 volts, and on the secondary we have a 12 volt center tap transformer. I'm using 2 outside legs, so that's going to give me 12 volts AC RMS. Now if I follow out one of the legs, you can see it's coming over here and it's going to the diode. On this side of the diode, I'm connected it to the anode side. On the cathode side of the diode over here, it is just feeding the light. On the other side of the light, it's coming back to the other side of the transformer. So let's go ahead and let's plug it in. Well, as you can see before, just like with the power supply, we have the light is on. You may not notice it in this, looking at this light now, but this light is not the brightness that it was before with the DC power supply. Let's take a look at some voltages and let's see what kind of comparison we can have here. Alright, the first thing we're going to look at is the output of the secondary of the transformer. So I'm going to be looking at the AC voltage there. So I've got one leg there, I'm looking there, and we have 15.32 volts. Okay, 15.32 volts. Now, let's go over to the DC and let's take a look at our output DC volts that's being fed to the light. So this is on the output of the diode. If I look at that, I see that I have 6.5 volts. So as we've shown from the whiteboard, first thing we have to do is we got to get a peak voltage. So let me see if we can show you guys this so you don't get a glare. So first we take our 15.32 volts, and that's our RMS volts. Okay, so now we're going to multiply that times the square root of 2, which is approximately equal to 1.414. So I'm going to say times 1.414, and that gives me 21.66. Now we have the drop across the diode, the voltage drop, so we're going to subtract out, say, 0.7 volts. That gives us that value, 20.96. But now when we want to calculate the DC average voltage when we're using a sine wave, then we take 31.8% of our peak. So now we'll say times 0.318, and that's going to be equal to 6.6 volts, which the voltmeter showed 6.5. So we're like within 1/10 of a volt. That makes a little sense, I hope. All right, so now hopefully you got a better understanding of a diode and how it works. Okay. And I think what we're going to do is the last thing I want to mention to you, just want to mention it to you about the diode. What you want to do is think of the diode. This is the P type, this is the N type, of course this is the anode, and this is the cathode. Okay. You hear some people say, well, the anode has to be positive and the cathode has to be negative. Alright? And for the circuits that I just showed you, that's true. But when it gets to, say, a battery charger, and say for the riding mower, the charging system, look at it like this. Let's say I had my AC source, which is the stator, and there's my diode, and here is my battery, right? Well, I got an AC source on this side, which is positive, and I got a DC source over here, which is my battery, which is positive. So now I got a positive and a positive. But now now it gets a little confusing. So instead of thinking that this diode needs to be positive over here and negative over here, think of it like this. The anode has to be more positive in respect to the cathode. For example, if I had 14 volts over here and I had 12 volts over here, both of them are positive, will the diode turn on? Yes, because this side is more positive in respect to this side, okay? Can you see that this side, if you can look at it, that the 12 volts, isn't it more negative in respect to this side? So it's less volts, even though it's positive, it's still going to turn on, even though we have a positive volts here and a positive volts here. Now, if I was to go and I went up, say, 16 volts, is this side more positive in respect to this side? No. Then the diode is not going to turn on. So just think of it like that. The diode, for it to turn on, the anode has to be more positive in respect to the cathode. Or if you want to turn it around the other way, you can say the cathode has to be more negative in respect to the anode. And then that way you don't have to worry about this has got to be negative volts over here and this has got to be positive, which it is true with the circuits I showed you, but in this case it will still work. You just have to think, I just like to think of it positive in respect to the cathode. Now a little bit later we're going to be looking at some waveforms, and these are waveforms I captured with the stator connector hooked up. And we're going to look at the DC volts, we're going to look at the AC volts. This is with the battery on it as a load. And then we're going to look at the, see what we can figure out from looking at these waveforms. In the final legs of this video, so let's go ahead and we'll wrap this thing up. Now this here is the, when the riding mower is running, the stator is hooked up. So it's just like everything is back to normal. Now this is over here where it's idling, this here is where it's wide open, and this is idling just as it was before.
Now notice that one thing here, that this here peak voltage runs all the way across, either whether it's in an idle condition or whether it's in a wide open throttle. And it looks to be about somewhere around, I don't know, about 16 volts thereabout. Alright, so that's one observation that we see. Let's go over to the looking at the idle over here. Now first the thing you notice is that, well, it doesn't quite look like a sine wave anymore. You see that it's kind of flattened across the top, a little bit rounded. Alright, it doesn't have that nice sine wave that we had when we disconnected the stator when it was unloaded. Also notice these here spikes that's running down here. If we take a look at those spikes at an idle condition, we're running about 38 volts there. Alright, well let's take a look at the it when it's wide open. Alright, so if we take a look at that spikes there, we're running about 107 volts there. Alright, so what is the reason for that? Well, the reason is that when we are passing current through a coils of wire, which is in this case is our stator, and that is an inductor, and when the current is passing through the coil of wire, and when you abruptly turn off that current, you will generate a high voltage spike, inductive kickback voltage, sometimes it's known. Okay, so let's take a look and see what's going on here with the DC charging voltage and the DC charging current. Well, if we take a look, we can see that if I'm right here looking at the green trace, you notice in this period right here where the line is flat, this is where the diode is turned off. But right in here, right at this point, it starts turning on, then it's falling down, and then it gets to here, and then it turns off. Well, notice how that when the diode turns on, look how it coincides up here with the stator voltage, right in that little corner. Well, let's take a look at it when it turns off. So when it turns off, and it turns off right there when this high voltage spike is created, and you notice that it's just this little area right in here that we're utilizing to when the diode is turned on. Alright, well now let's take a look at the diode when it's turned off. If I come down here in this area, line up the cursor on this area flat, you notice that in our videos that we had that when the diode turned off with the little circuits that we showed, that when we use a test light, and when the diode turned off and across our load, we basically had 0 volts. Well, in this case, the battery is our load. So when the diode turns off, as it is right now, notice that we have a voltage of 13.14 volts. Well, this voltage is the voltage that's directly across the battery when the stator is pretty much out of the circuit. All right. Now let's take a look at some of these here voltages for the DC charging volts, and let's look at the amps. Now, to save us a little bit of time, the video is getting a little bit long anyway, let's just go ahead and let Picoscope take care of measuring this out for us, and then we'll do a comparison to see what we had with our own measurements with the voltmeter and the amp meter. So let's just say I put one right there, and maybe I'll put one right there. Kind of get it there. Okay, so let's go ahead. We're going to add a measurement, and we're going to do the DC charging voltage first. So that's the C channel. I want the DC average. I want it between the rulers, and let's see what we get. So I got a voltage here of 13.66 volts, and for me it looks like I got a voltage of 13.77 volts. That looks pretty good. Okay, let's go ahead and let's get us another measurement. This one here is going to be for the DC charging current. So let's go down to D, and let's get our DC average, and let's get it between the rulers, and let's see what we got. Well, I got a 2.957. That's the measurement. And for my measurement to what I got a 3.15. So we're very close. So it all looks like it's doing pretty good here. Okay, if you have any other questions about this here, just let me know. And this is going to wrap this video up. And if you enjoyed the videos and like to see more, be sure to subscribe to the channel. And we'll see you guys in the next one. You take care.